Hello there, everyone, and welcome. This is Professor Thayer with you here today to talk to you about physical chemistry for the life sciences. This will be our first lecture in a series of lectures on this, constituting our PCLS class here at Wesleyan University. The first lecture today will be on the dawn of quantum mechanics. So how this is going to work is I'm going to share my screen with you, and I will be using my new Dell Touch laptop, which I'm on, well, at least it's new to me, and a snazzy new pen that goes with this. And I'll be putting some notes on a whiteboard. So I encourage you to follow along and take some notes in your notebook. So I'm going to turn turn the video off and then go ahead and share the screen. So just bear with me for a sec. So I get started. This is all a bit new to me, including working with the touch pen. So hopefully everything is going to go as planned, but do just bear with me if there are any glitches here. I've done a few dry runs, so hopefully this is all gonna work pretty okay. Let's share the entire screen here. As I touch this and it doesn't seem to like activate. All right, so hopefully I should be sharing screen now. It says you are screen sharing. Great. Okay, so you should be able to see I have a blank document here, and we're gonna go ahead and do this. Let's put this full screen for us. All right, so today, said we're going to talk about the dawn of quantum theory. Let's put that on lecture one. Lecture one, dawn of quantum mechanics and quantum theory. So, was a very interesting statement made by Albert A. Michelson of the University of Chicago in 1894. 1894, of course, was the end of the 1800s. People were feeling pretty good. We had completed the Civil War. We had developed physics. The world was enchanted by the World Fair. People were feeling pretty good about things. Michelson said the more important fundamental laws and facts of physical science have all been discovered, and these are now so firmly established that the possibility of their ever being supplanted in consequence of new discoveries is exceedingly remote. Basically, we already know everything. So if you've considered about taking this class, if you've taken any advanced physics classes, you'll know that much of the discoveries that underlie modern physics and our modern understanding of how the world works have been made since that date. But interestingly enough, Michelson, in fact, contributed to a lot of the work underlying this change in the way people viewed the world. So let's just consider what his experiment contributed. Let's consider some of the important discoveries that had been made and firmly established at that time. And then we will see, as the course unfolds, how these inventions and understandings of how the world works were important to the working of quantum mechanics. So Michelson and Morley did a famous experiment you may have learned about. I learned about it in Gen Chem for many years ago. And the idea was an experiment to measure the speed of light. And this had to do with the question of whether do we need an ether, a medium, to propagate that wave. Now, why was that an important question? Well, let's consider other kinds of waves that you might be familiar with. For example, sound waves. You may be aware that as sound propagates through different media, it travels at different rates depending upon the density of it, and also the Doppler effect. If you hear a siren coming towards you versus the siren leaving you, you will hear that the sound of the pitch of the sound that is emitted would be different. It will be higher frequency approaching and lower frequency as it travels away. Just spend some time in a major city and be near a siren and you can witness this for yourself. But the interesting thing is that the speed of light one did not depend on a medium. In other words, it can propagate through a vacuum. And two, was constant. Now, there was this idea that there is such a thing as the ether. You may have heard about this. I guess it sort of was supposed to be the air, or like, I don't know, some fluid that the earth was embedded in as it rotated throughout the heavens, something like this. And the idea was that since the earth is rotating around the sun, as it moves, it would produce a kind of a Doppler effect, just like sound would, if in fact it required going through medium. But Michael Morley set up these experiments where they were using some mirrors and large distances in order to send some light beams over large distances, and having precision instruments to actually measure the time it took for that to travel. And they found that there was no evidence for that whatsoever. And this laid the groundwork for none other than Albert Einstein's special relativity. Talking about early, this would be 1905, for example, for which, of course, he won the Nobel. Constant, and we have the speed of light as a constant, and we would have this. And also, so his work established c speed of light as a universal constant. And also gave the idea of particle wave. Well, this itself didn't, Einstein's work didn't necessarily. The particle wave duality was also coming into play, which we'll talk about momentarily. All right, so what other accomplishments did we have at this time? What other accomplishments were there at this time? So quite a few in the world of chemistry. We had Stanislas Cannizzaro established the existence of the molecule. But you remember in the 1800s and so and such, people were not too sure that there was such thing as the atom even. Dmitry Mendeleev, Russian, organization of the periodic table. But it's important to realize that although they realized they were these periodic properties of the elements, that they didn't know why they were periodic. And of course, the question was, well, how come? And quantum mechanics will answer this question. We'll come back to that later in the course to explain why they're actually periodic, although you may have some idea from your Gen Chem class. We also have Friedrich Kekulé, who in the dream figured out about benzene ring. Benzene ring, aromaticity. So you probably heard about this in your organic chemistry class. We have the pi electron clouds with conjugation around the ring. So that was an important thing. All right, now physics. Had quite a few. So Isaac Newton. So we all know about the falling apple, right? So he worked out the Newtonian dynamics. You may not know about is he also invented the calculus. If you didn't enjoy multivariable or regular calculus, you can complain to Isaac Newton about that one, which he needed to develop in order to describe the Newtonian dynamics. And also you have Comte Joseph Lagrange and Sir Walter Hamilton. Did you ever hear of Lagrange multipliers? Lagrange and Hamilton. So Hamilton also invented a version of calculus. In fact, actually, we tend to use Hamilton's calculus more so than we do Newton's in terms of the notation. This is why we have those different notations for the primes and the ddx kind of stuff. They're the different approaches they took. So they were both mathematicians slash physicists. And so they were able to apply the Newton dynamics to a number of other fields, such as planetary motion, elasticity, and hydrodynamics. All right. Mount Rumford, James Joule. Did you ever hear of the Joule measure of energy? What did he do? He was involved in the equivalence of heat and work. You'll be hearing much more from Joule's work when we talk about thermodynamics. We also had Sadi Carnot, French. Formulation of the entropy and the second law of thermodynamics. We also have much more to hear from Carnot and to hear about the Carnot cycle. Josiah Willard Gibbs. He worked at Yale and is a native of New Haven. He's actually buried there, and you can go and visit his grave, which I've done. He formulated most of thermodynamics. Have you ever heard of Gibbs free energy, the delta G? That's this guy. Okay, and then we also have the fields of electricity and magnetism. Also more hints that something was amiss. James Clerk Maxwell. He unified optics with electricity and magnetism. We also have Heinrich Hertz. Have you heard of the HZ or frequency? That's for this one, this guy. Demonstrated wave-like properties of light. Very important for particle wave duality. So as you can see coming out of this, certainly there have been a lot of accomplishments. Many of the modern things that we know and love about physics and our understanding of the world had already been established now 150 years ago now. And so that's what prompted that famous declaration where it was stated that there really wasn't anything more to learn. Would you be encouraging your students to be going into physics at this point if all these things were already solved? The idea was that, oh, we'd just calculate these things out to the nth decimal place. But, you know, it's really more for technicians and could work on instrumentation, but there won't be any more theory to do here. That was very much the idea that that Michelson had, and that was very much the prevailing vision. However, there were a number of things that were a little bit amiss. So we're going to go through about some hints that classical dynamics might not be enough. Let's see. Okay. Case study number 1. Black body radiation. Now, what's a black body? Well, a black body is an idealized material that when it gets heated up, it's going to be emitting radiation. When a black body is heated, the color is going to change, and the emitted radiation is black body radiation. So you think, well, what kind of a material is that? Think about blacksmiths hammering metal. So when you heat up, so to agree, metal, when under normal circumstances, as we see it in our daily lives, is not emitting any colors. But if you take metal and you heat it up, it will start to glow. This is what we're talking about. This is a radiating body, and metal can behave as a black body. And so this is where we're getting this idea. Now, so this is what it's going to look like. So example would be metal. Of course, metal is not perfect, but gives you an idea of what a black body would be like. So we're going to have this range like so of increasing temperature. Okay, we have this idea in our heads that when something is red hot, it's really hot. But in fact, actually, red is the lower temperature. So we have cooler, we're going to have a low frequency. And what do we mean? So this is new. This is like a B for frequency, right? This is frequency. And so we have this idea that red is very hot. Well, it is hot enough to start the emission process, right? But in fact, actually, blue is the hottest, which we may colloquially think is cold, but that's not quite right. It goes red to bright red to white to blue. Pretend that's evenly spaced. All right, great. This is the hotter end of the scale, and this is this high frequency. Black, let's just capture that thought out with a black body. definition of a black body is an ideal material which absorbs and emits all frequency. All right, so let's think about the graph of the black body radiation. So we might want to make a prediction of classical physics, and we might want to make the graph of this. So prediction of classical physics. Classical physics says the intensity of the light would go proportional to the frequency. So we can look at the Rayleigh-Jeans equation. So we're going to say P of U and T. All these are supposed to be pieces of the density. Equals. I'll explain all these momentarily over C cubed V squared dV. All right. All right, so what does all of this mean? This says the change in the density as a function of the wavelength and the temperature. We would reworded this. All right, so we could also, so this would be for the multivariable version, and then we could say if we hold the frequency constant, and we're going to look at the temperature dependent version of this, would be given by this equation. So 8 pi, those are just numbers. C cubed, this is the speed of light. KBT, this is the Boltzmann factor, which we'll say a lot more about coming up. This comes from statistical mechanics, and T, of course, is just temperature. And V squared, this says this is the frequency squared as we go over the different frequencies. So what exactly, what is the thing that does that? So you might be wondering, well, what the heck does this mean in the great formula? Well, what does it mean about the density of the radiation? It's light. It's the intensity of the light, okay? So this says the intensity of the light. The intensity as a function of the frequency. This is intensity of the light emitted. That's what the I is about. Equals this equation up here. Okay, so in other words, this is a quadratic equation. You see that V squared, it's quadratic. So let's go ahead and make a graph. All right, well, we said it's like that. Let's make a graph here. All right, so we're gonna put the intensity here, and we're gonna put the frequency down here. Why are we doing this? Because look, it's PV, it's over the V's, right? dV. So we're gonna do the, which is the V's. All right. So we're gonna put that here, and we're gonna go from red to blue, just like we did before. All right. So when we actually take a look at these bodies, we're going to see something like this. Now what we're gonna do is we're gonna get it at the different temperatures. All right, so let's go ahead and do this. Let's see, that's the max. That's gonna be something like that. Okay. I hope I spell. Okay, we're gonna do another one like this. Extend this axis over here, so we have a maximum here. So this trace is, let's say it's 400 Kelvin. Let's say this one is 500 Kelvin, and then we're gonna do 600 Kelvin, right? Kelvin is just a measure of temperature. So it's basically getting hotter, right? That's the idea here. All right, so we see that these are at having their peak at various frequencies. So that is this is what we actually observe. But when we do the classical one, I'm gonna do this one in a different color. This is the classical view. Goes as v squared, right? So as we said up here, it's a parabola. And so that diverges to infinity. That's impossible. What's going on here? All right, so we see that there is a bit of a problem here. Somebody didn't get the answer quite right. All right, so let's just recap the summary of the black body problem. So in other words, this can't be the correct equation. But using only just what was available from classical, we didn't know how to solve it. So classical physics says that it should be in the form of kx squared. For radiant energy. It's the parabola, right? Okay. This diverges to infinity. As the frequency approaches infinity. This means approaches, if you remember calculus, approaches infinity. And what this says is the black body will radiate an infinite amount of energy. What is all the energy crisis about? Looks like we're going to be great. We can produce as much energy as we want. Doesn't seem quite right. This is impossible. Impossible. We used to have posible or impossible in Spanish class. Impossible. All right. What's going on? Major clue that something's wrong here. Something is wrong here. All right. Next clue. Oh, no. Next Planck. Planck to the rescue. We'll have more to say about all of this as we progress through our quantum mechanics discussions. But let's just talk about it in more general terms today. Planck had a great idea. Suppose a phenomenon is caused by the oscillation of electrons, just like it happens in radio. So when you have radio waves and you're going to capture them in an antenna, the electrons are going to be oscillating about. Physicists tell us that this is what happens. But maybe it's like that. Maybe it's about oscillating electrons like radio waves. Like radio antennas. So what's needed for this is for the energies to take specific values. In other words, we'd have this equation here, which you've probably encountered at some point in your high school physics or something. NHV, this is energy. This is integer. The H is Planck's constant. And this is the frequency, right? That's what this equation stands for. So using this idea along with statistical thermodynamics, which we're going to be talking about throughout this course, Planck derived a new equation for black body radiation. It's this one. Rho of B and T equals P. So now we're going to hold the frequency constants T dV, just as we did before, equals, now we have a new formula, which made more sense. All right, I'll just write it down here for a little more space. 8 pi h, that's Planck's constant, over c cubed, speed of light, times, oops, sorry, frequency, not W, frequency cubed, dV, over E, that's natural E, H, E. In case you don't remember about E, it's just a natural constant. You can just look up the number, KV T at -1, like so. So this was widely rejected in the beginning. So you said, what is going on? Are you really sure it's all about this quantization? Where's the quantization in here, by the way? Anyways. So we see that this has Planck's constant. It's, sorry, this should be an N. Make sure you got that as an N. All right, good. Here's your quantization. All right, and so we see that this involves then the quantization, which led to a different kind of equation. And black body radiation actually followed that, which is great. All right, case study number 2. Photoelectric effect. Albert Einstein won the Nobel Prize for this. He won more than one Nobel Prize. Einstein explained the photoelectric effect also using quantization, which is why it was really important. I'm just going to draw a little diagram here. I'm even going to just put a little sun up here. Let's think about the sun. I don't want the cold weather the last few days. I think that kind of looking like a star. We could even give the sun some sunglasses. There he is, giving off some radiation. Okay, and we have some UV light coming from the sun. We know this. Get a sunburn if you don't wear your sunscreen. Don't get cancer. And this here is not a beach blanket. It is a metal. Ever had a solar powered calculator, or this here watch I have is solar powered. This is exactly how it works. This is from Becquerel. Studied the effective light in photovoltaic cells. In other words, like solar panels, which is another example. The idea is when the UV light comes and strikes a metal, electrons jump off. And you could collect those electrons and capture them in wires and use the electricity. Sounds pretty cool. Free energy, right? UV light causes electrons to be ejected from metallic surfaces. Seems interesting. So the problem with this, they noticed, was that according to classical mechanics, did not quite work as expected. Contradictions. Classical view. So just like when people were studying the black body, and they noticed this doesn't really quite line up. But the same thing was going on with the photoelectric effect. Okay, kinetic energy of electrons is independent of the intensity of the UV radiation. So you might be thinking, all right, well, how will I get more electricity? Well, maybe I should put it in a brighter light. That might be the ticket, right? It seems like, that would make a lot of sense. But this says it's independent of that. There's not a threshold intensity. So you might think, well, how come I'm not getting any electricity out of my solar panels? It might be because the sun's not bright enough. Well, yes, I mean, to some extent, there is some intensity needed, but it's really more about the frequency. There is not the threshold intensity I. Meaning to get the electrons to come off, but rather the threshold frequency E0. Characteristic of the metal for the electrons to be ejected. So this will take them off and actually be able to use them. So this seems kind of interesting. So Einstein observations where radiation itself is quantized. And radiation exists in package of energies. You heard that before? Photons. Ta-da. So we can then write an equation to explain this. So we might say the kinetic energy of the ejected electrons is equal to the energy of the incident UV light minus the amount of work that got done for it to get ejected. So let's see if we can put that into some kind of a formula. So let's write out the formula. 1/2 mv. This is normal V. There's a lot of V's here. You'd think with all the letters in the alphabet, they would have picked a different one. N H V. I'm trying to make it look a little different. Minus H V0. All right, let's unpack this. This here is the kinetic energy of ejected electron, right? 1/2 mv squared. You heard of this equation before from kinematic equations, physics or calculus. Great, that's what that one is. And this is the energy of the incident UV light. Okay, so this is an integer, h, that's Planck's. Right, that's the Planck's constant. This is frequency here. Right, this one is frequency. And let's just be clear that this one is velocity. Not to confuse them, right? So this is the fancy V, and this is plain V, just in case you can't tell that from looking at it. And this is also frequency. Frequency right here. Okay, V0, incident frequency. So this is the amount of work done. This is a work function. All right, so it should hopefully make sense. So we say how much energy does the particle have? So amount of energy that went in minus the amount of energy that was expended. That is the amount that was used to do work. So we have the difference of those two terms. The incident amount of energy from the light is NHV or NH nu, and then we have HV0. This is our work function. So that's the amount of energy that got lost for the ejection to occur. And so the kinetic energy is going to be equal to 1/2 mv squared, as we know from before, from calculus and physics. And that's how we can write out this equation, and that's what that means. And the interesting thing is that Einstein independently got the same value of H as Planck did, which is interesting. I mean, we call it Planck's constant, but actually in this case it was Einstein's constant, but Planck had published first, so we call it Planck's constant. But anyways, that was an interesting observation, and also led some more credence to what was going on here. The quantization, in fact, actually was taking place. Now let's just do this. We have this right here. This then is where the quantization is happening. All right, so that's our second case study. Now I have another one, case study number 3. Things that were amiss, line spectra. All right, so what is the line spectra phenomenon? In fact, you could actually observe the line spectrum phenomenon yourself. So atoms, when they're subjected to an increase of temperature or electricity, will emit electromagnetic radiation with a characteristic discrete frequency. Fluorescent light bulbs is a great example of that. And this is where you may have noticed this before. I used to teach Gen Chem, and we'd take out these little tubes with the little film on it, and you could look at the line spectra from the fluorescent lights. Atoms, when subjected physically prism to an increase in temperature or electricity, emit electromagnetic radiation with a characteristic discrete frequency. How do we talk about full spectrum lighting when we talk about light bulbs? Of course, the sun is a full spectrum emitter, but when we look at the light bulbs, particularly the ones that are fluorescent, it's not full spectrum. It means that you have only a specific kind of an atom, and they're not all emitting, so you don't get all the colors for the white light, and that's what we mean by that. Vision spectrum makes a line pattern. because when you emit and you get the full spectrum, right, you have the complete spectrum, right? Put some light between the prism, right? Light comes in and then it gets shines out. So if it's full spectrum, you see all the colors, red to blue, right? But if you only get certain ones, so if the incident beam doesn't contain all of them, there may only be certain ones that show up. And each of those is what's characteristic. So that's what we're talking about here. So scientists believe that line spectra are telling something about the atomic structure. They didn't know what. But what? Might know from your Gen Chem classes if you were paying attention. All right, so let's now consider some empirical observations. So we have Farmer. So what Balmer noticed is the frequency of the lines in the hydrogen spectrum fits this equation. Equals 109 680 1 over 2 squared minus 1 over n squared cm to the minus 1, where n takes on the values of 3, 4, 5. It's a little quantized there, needing some integer values here. V squiggle equals 1 over lambda, which is the wavelength, which is equal to V over C. This is again our speed of light, right? Lambda is the wavelength. That's curious. All right, let's leave that for a moment and let's see Rydberg also had some observation. So Rydberg drives the general form of the Balmer equation. So all line spectra of H can be accounted for by considering the difference of two terms for which Balmer had held one constant. But Rydberg looked at this from a bit of a more higher up perspective, and he took a look at this for not holding one of them constant. So he did different states. So he came up with this equation: V squiggle equals R sub H. This will be a Rydberg constant, which I'll tell you in a moment. 1 over n squared, again, quantization, minus n1 squared minus 1 over n2 squared, or n is integers, or n2 is greater than n1. All right. RH takes the value of 109 677.581 centimeters to the minus 1. Oh yes, that could have been, this is the refined version. This could have been expressed in hertz. Let's take a look at what all of this means. So inner energy level. 1, 2, 3. All right, yeah, I draw the right number of circles. Okay, so here is n equal, this is n equals 1, n equals 2, and this is the n equals 3. Now you probably know where I'm going with this if you've taken Gen Chem. All right, so as we go up to here and then we come back down, we have one level. This level here. And I need one more circle out here. So, all right, so when an atom becomes electrocuted, electricity runs through it, would jump from one energy level up. This is the ground state. It can jump up, and then as the electron comes back down, it's able to radiate energy, which I'm showing by this squiggly arrow. So this would be from n equals 1 up to 2 and then back down, right? Then we go from 1 to 3 and back down, and this is 1 to 4 and back down. All right, then we could also start at energy level 2 and promote that one up and come back down to 2. We could go up to 3 and come back down from here. And also we could have this series here where we go from n equals 3 up, n equals 4 and back down. And of course, this could be even more complicated depending which atom we're talking about. So the ground state transitions then are going to be all of the transitions that are being illustrated here in the start at the lower level, right? That's what makes this be a ground state transition. So these are your ground state transitions. Then we also have the Balmer series. So these are the Balmer series. There are only 2 of them in this scenario. There are three ground state because you're above the ground state, right? There's fewer combinatorics available. This is the Balmer series. And above the ground state transition is this one over here. So then this is another category here. Raman, Balmer, and Passion series is how they're called. So what this tells us then is the ends denote the energy state. Of electrons. It describes the electrons as they move from an upper energy down to a lower one, right? Because first they have to go up, but the radiation occurs when they go back down. That's the observable. You can't see how high it goes up. We know about it because when it comes back down. An upper energy level to lower. N equals 1 is the ground state. Electron heat or spark. Electricity, right? That's how I put it. The fact that the H spectrum has lines rather than a continuous values, then suggests that electrons have discrete allowed energies. Discrete. Once again, this shows the idea of quantization. So this quantization keeps coming up. Understanding electron structure. Of course, they didn't actually know why that was happening. All right. Next clue. We de Broglie. Matter has wave-like properties. De Broglie wavelength. You heard of this? This led to the idea of a wave duality. Somehow light is different than other kinds of waves. Suppose that if light can be particle-like, then so too matter could be wave-like. So de Broglie's idea here is that matter obeys Einstein's equation too. It's not only applicable to electromagnetic radiation. So we can have this lambda equals Planck's over the density. So we start with Einstein's equation for electromagnetic radiation. And we have P equals mv, momentum. This is momentum. And this is regular velocity. P equals mv. Substitute that in for this P. Oops, hey, all right. So then we can do the equals, this is his insight, Planck's constant over mv. Huh, interesting. Right, so this is wavelength. And P for all of these is momentum. We had P for density earlier on, which I tried to draw a little bit different, but you may not get the different fonts. I can write it. All right, so this led to then the Bohr experiment, the Bohr theory of the H atom. Is it plum pudding or is it a compact center model? All right, we need to tell these two things apart. And he came up with an interesting experiment to do this. So we're going to have plum pudding versus the compact center model. So the plum pudding model says, okay, here's an atom, and we're going to bombard this with alpha 2 plus particles, beams, and this is going to have some fill in here. So I'm just kind of this, so it's kind of a whoosh in here. Maybe it's like a whooshy P or something like that. All right, so there's some whooshiness in there, and there are gonna be some electrons in various places, just kind of floating around, just like when you have a plum pudding pie, that you would have the plums be spread throughout the pie. Electrons might be something like that. So, and these are your beams going through. So how often would you hit? E minus embedded in a diffuse field. Uniform field. Uniform beam. That's what you would expect. So as the beam goes through, the probability to hit an electron would be about the same for all of them. So you wouldn't really expect to have much variation in the beam. All right. However, if you had a compact center model, that might look something like this. There's a nucleus. It's full of pluses. Dense nucleus. All right, let's make it a little more quantitative here. I'm gonna do 5. So we say there's 5 pluses in here, right? And we'll have 5 minuses spread throughout over here. These are the electrons, and the beam will go through. Now keep in mind there's the 2 plus alpha beam, and what's going to happen is when this beam comes in and whacks this, the pluses are going to repel because it's alpha 2 plus. Same charge is going to repel, so you'll have this one coming off, but the others will more or less pass through. Okay, there is a dense nucleus. So the positive nucleus will repel, right? So this right here is the plus nucleus will repel the alpha 2 plus beam and cause a deflection. A regular deflection. So in this case, you wouldn't really get a lot of deflection because the beam is going to be spread across all the pluses, right? And so it's not really going to come off that often. Really, it should just be uniform, but there shouldn't be any deflection. Here you will get mostly not deflected, but there will be some deflection. This one right here exists, and that's the key thing that will happen. So the question is, which of these is true? And we could see this by doing an emission experiment. So this was Rutherford's experiment. And we're going to have a beam generator here. Right, it's the beam generator. It's exactly how it looked. It's a cardboard box, just like so. Right, okay, beam generator. So an alpha 2 plus comes out, and you have some kind of a wafer thin paper here, right? So this beam is coming onto this paper like so. This is wafer thin material, and you have a screen going around it like this. Something like that. Okay, this is the screen. And so you're hitting lots of atoms in here, and the question is what's going on? And you get occasional spots, very specific spots, just a couple. Here we're looking at the back side of the screen. It's a couple of spots. And of course, most of the beam will just pass on through. So you're going to have a giant spot over here. Most particles pass through. Occasional reflection spots, like X-ray crystallography did here. So it's going to be dense nucleus. Model is the winner. All right, so next thing we need to talk about then is some contributions from Bohr. Bohr introduced non-classical assumptions. When assume the existence of stationary electron orbits. Stationary with an E is for writing with pens. A is for standing still. Assume the de Broglie wavelength must fit around the orbit. Let's see what this looks like and why is this true. This is circles mean a lot of things in these diagrams. These circles are an electron orbit. Not an atom. So we're looking at one electron. All right, I'm just going to help myself to draw the picture better. These dots don't, in fact, really mean much. All right, so I'm going to just use this to help me draw diagram more to size here. Okay, so this is waves going around in a circle, right? So you might have a wave oscillation on a line. Here we're doing a wave oscillation in a circle. This is in phase. in phase oscillation is being shown here. But if we add an out of phase one, let's draw a picture of what that would look like. So it's like this. All right, the point is there is this. This is the key thing we're looking at, right? By not can, so when these are exactly in phase, that means it keeps going around and around in exactly the same way. It's like spirograph, if you ever played with that toy. If you line up, you go exactly the same every single time and makes a boring spirograph picture. But being out of phase makes interesting spirograph, but bad things here. By not canceling each other out, the electron waves do not lose energy. And therefore they do not crash into the nucleus. Wait, let me try this one. Yeah. This does not happen. All right, so let's just take a moment to look at this. This is what actually happens when the waves are oscillating around the central orbit here. The waves are going to be in phase. If the waves were not in phase, as is being depicted over in this middle one, the problem is that the waves would cancel each other out, right? Because you see, it would start going in a different place. And so because of the canceling out, they would lose energy. And then it would, so if the electron lost energy as it's doing a classical orbit, what will happen? Well, it won't have as much energy, and so it's going to get sucked into the nucleus, and the atom's going to collapse. And so, atoms are still here, and they've been here for a really long time. So that can't be right. So this argues for the idea that electrons must be in phase and they must not cancel each other out because atoms, in fact, exist and don't crash. All right, few pieces of final information here. All right, so I'm going to give you a couple of equations that then resulted from these observations. So the radius is quantized, so the radius equals 4 pi E0 and squared h bar squared over m e squared for n equals 1, 2, 3, blah, blah. Okay, so this says the radius is quantized. And perhaps more importantly, the energy is quantized. So the energy of an orbital equals negative mass of an electron, natural e to the 4th power over 8 E0 squared h squared times 1 over n squared, or so one can derive these, n equals 1, 2, 3. This is energy levels. The energy levels E sub n are quantized and so one can also then calculate the delta E, change in the energy level, equals me e to the fourth over 8e0 squared Planck's, oh no, Planck's without the bar, sorry, Planck's, plain Planck's, h squared 1 over n1 squared. Oh, this looks kind of like a formula we saw earlier in the lecture. Rydberg's equation equals hv. This gives rise to lines of the H spectra. Those ones we saw with Balmer and we saw the Rydberg equation. They are due to the quantization of energy levels. Quantization of energy levels. Where we see those energy levels coming out as an integer. Sorry, that's a B here, just in case that's not totally clear. All right. Frequency. So you see that we've come full circle on this whole line spectra, the hydrogen business. All right. And so one final thought then on all of this is the Heisenberg uncertainty principle. All right, so the position and momentum of a particle cannot be specified simultaneously with unlimited precision. Probably heard this before. But let's try to understand why. Position and momentum of a particle cannot be specified simultaneously with unlimited precision. All right, so now we have this idea that electrons are whizzing around the nucleus. The nucleus has dense and has the pluses in there, and electrons are buzzing around it. And they're in these waves that are going in orbits. And you might want to know where the electrons are actually at. They're moving around. And so people started to want to actually go in and to try to do this. So how would you do it? Well, you'd have some measuring device, just like we saw with the Rutherford experiment, where you would send in some kind of a particle and you'd try to bombard it, and then occasionally it would bounce off and you would measure the location. So you'd have to use a photon of light in order to do this. So let's think about how spectroscopy works to see things, say, with like a light microscope. So when you have an incident light to look in the microscope, the light waves are oscillating, right? And they bombard the particle and then they bounce off, and that's how you actually see things. But if the wavelength were too big, the problem would be that you wouldn't be able to see it. Or in other words, if the particle were too small, you wouldn't be able to see it. So just because you like magnify something more and more doesn't mean you're going to be able to see subatomic particles using a light microscope. And this is why we move to things with wavelengths that are more appropriately sized, right? But they're higher energy. So that's just a basic idea about how you would see things, that the wavelength needs to be an appropriate size to the thing you're trying to see. So if you want to see something that's smaller, what do? Well, you make the wavelength smaller too, right? Electrons are pretty tiny. You're not going to see those with regular light. Even if you had a giant magnifying glass, you're still not going to be able to see electrons with incident light because it's going to bombard the particles so infrequently that you're not going to see it. So well, what do? You make it smaller and smaller, but the problem is that it's going to be higher and higher energy. And the idea is if you use higher energy to bump the electron to see it, you're going to kick it out of orbit, so you won't be able to see it. So you'll never be able to do that. Therefore, it is not possible to know how much momentum the electron already had. And how much is acquired through the measurement collision. The position and momentum. And let's just mention that the momentum equals mv, right? So the mass stays constant. We talked about it more like, I made an argument that it was more velocity based, but really that's a proxy for talking about the momentum, which is related to the velocity. The momentum are never exactly known. Simultaneously, right? So you can't know those. So that can be expressed as delta x, delta p is greater than or equal to Planck's constant. Uncertainty in position. Uncertainty of momentum. And that's Planck's, which equally could have been called Einstein's. All right, so then in summary, we have taken a look at a number of things here. We started to see that classical mechanics had been well established in physics. Although classical mechanics had been well worked out from Newton and others after him, it didn't exactly explain all of the things that scientists were being able to actually observe in the early 1900s, late 1800s, early 1900s. People started to get better instruments, better ways of actually detecting things, and we started to notice that some things really just weren't exactly following the way that classical mechanics went, particularly things pertaining to light. It seems that somehow light was unlike other phenomena that had been studied before. It wasn't really like sound waves, it didn't have to go through a medium. It always traveled at the same rate, regardless of going with or in the direction of or opposite to the Earth's spin. So Doppler effect didn't work anymore. And then we started seeing about the particle wave duality, that it had some wave-like properties and some particle-like properties. It was really something quite different. And then we had the insight about, well, maybe all things actually behave this way. maybe there's a new kind of a physics. And this is really what paved the way for this new idea of quantum physics, which of course for us is important because when we're working at the subatomic level, that is with electrons and protons, the quantum mechanical aspect of the world really becomes really quite important. So we saw how there were a number of things that were just not quite adding up. We saw black body radiation as an example of this. Um, we saw the line spectra, the hydrogen, as being another example of things not quite right. And so we also started to see how some of these things then led to the tail end of the classical physicists as the new quantum mechanics physicists started to trickle in onto these things. Einstein, we all think is, amazing scientist, but he was really right at the cusp of that happening and transitioning into that new way of understanding how things actually worked. And so today what we've looked at is a lot of that groundwork of how that happened and how the idea of quantum mechanics started to trickle into the minds of some of the brilliant scientists that were absolutely instrumental in bringing all of this about, and started to see how quantum mechanics might start to work. So as we move forward in the semester, we'll actually be revisiting a lot of these things. We'll be revisiting a lot of the major contributions of the scientists who laid the groundwork, because a lot of those things are going to contribute to our understanding of statistical mechanics, thermodynamics, topics that are coming up in the second half of the course. And also much of the first half of the course is going to then be focused, maybe about say like a third or so will be focused on the quantum mechanical aspects, where we're going to work through some of the more specifics about what the implications of all of these things are, and hopefully give you a deeper understanding of those things we told you in Gen Chem, and kind of just expected you to accept these things without really a whole lot of proof. That's one thing that's really neat about physical chemistry, is that it really is starting to give some insight into why all those rules and laws and formulas that we learn in some of the lower grades in fact are there, and give some insight into how scientists actually figured this out. Why is this true? Because Professor Thayer said so. I mean, that's not really a very satisfying answer. So perhaps getting some insight into what some of the other scientists had to say, looking at a few of their experiments and gaining some insight into how all of that works, and why we teach you the things we do, and how you can understand and rationalize these things for yourself are some of the things that I would really like you to walk away from this course with. So I hope that this has been a great start to that journey. I hope you enjoyed learning a little bit about how quantum mechanics all began, and I really am looking forward to our continued discussions on quantum mechanics and the rest of physical chemistry, which are all part of the big same thing. Thanks so much for joining us today. We hope you enjoyed it, and we will talk to you again in our next meeting. Bye-bye.